In this video, we'll run a simple logistic regression with one categorical independent variable using the Youth Cohort Study of England and Wales 2004 to 2007 Cohort 12 dataset. This dataset is available for free download from the UK Data Service website. Let's say we wanted to answer the following question. What are the odds that young people satisfied with their work, education, or training placements in Sweep 1 of the Youth Cohort Study will be enrolled in education full-time in Sweep 2? Our variable of interest is S2Q10, a measure of enrollment in full-time education in Sweep 2 of the Youth Cohort Study. It's a binary categorical variable, meaning that it has two categories. This means we can model it using the logistic regression model, which requires a binary variable as the outcome or dependent variable. Because we are interested in the influence of placement satisfaction on full-time educational enrollment, we'll use S1Q4 as our independent variable, as it's a measure of placement satisfaction. Before we run our logistic regression, we should run some exploratory bivariate analysis to get some answers about the relationship between S1Q4 and S2Q10. If our independent variable was continuous, we would use a t-test to compare means. However, our independent variable S1Q4 is categorical, so we'll start by running cross-tabulations. Select Analyze, Descriptive Statistics, and then cross-tabs. Next, move S2Q10 to the columns box and S1Q4 to the rows box. We're going to click the Statistics button and select chi-square because this is the significance test we're going to perform on this relationship, and then click Continue. And because we're curious about S1Q4, we should also see some row percentages. So we'll click on Cells, and then under the percentages header, we'll click Row. Click Continue, and then OK to run the cross-tabulation. In your output window, you should have three output tables. The first output table is the Case Processing Summary table. It shows you how many cases were included in your cross-tabulation and chi-square, how many cases were excluded or coded as missing, and how many cases you have in total in your survey. In the second output table, you have the results of your cross-tabulation, so you can see how many students were satisfied with their placement and how many were enrolled in full-time education, how many were not satisfied with their placement and how many were not enrolled in full-time education, and also the percentages for each of these cells. And then in the final output table, you have the results of your chi-square test. We can see that in this chi-square test output table, the p-value result for the chi-square examining the relationship between S1Q4 and S2Q10 is 0.000, meaning that the relationship between these two variables is statistically significant. This is because for chi-square tests, the p-value threshold for significance is 0.05, which means that our result here is significant. Now that we know that our relationship between S1Q4 and S2Q10 is significant, we can fit our logistic regression model using S2Q10 as the dependent variable and S1Q4 as the independent variable. First, we'll select Analyze, Regression, and Binary Logistic. Find S2Q10 in the variable list and move it to the dependent text box as it's our dependent variable. Next, we'll find S1Q4 and move it to the covariates or independent text box. And because S1Q4 is a categorical variable, we have to tell SPSS to create dummy variables for each of the categories in S1Q4. SPSS does this for us in logistic regression, which is different than in linear regression when we have to create these dummies ourselves. To tell SPSS that S1Q4 is a categorical variable, click on Categorical in the upper right-hand corner of this logistic regression text box. Then move S1Q4 from the covariates text box to the categorical covariates text box, and then click Continue. Now this original logistic regression dialog box should have S1Q4 cat in the covariates text box. We can also have SPSS calculate confidence intervals for S1Q4. In the logistic regression dialog box you have open, click Options, and under Statistics and Plots, we'll click CI for XB. We'll keep it at 95% so that we can calculate a 95% confidence interval. Then we'll click Continue and OK. And now we can examine the output of our logistic regression. So you can see here that in the case processing summary, again, it shows us how many cases were included, how many were excluded, and how many we have in total in our survey. In the dependent variable encoding table, you can see that the enrollment in full-time education, yes, has been coded as 0, and not being enrolled in full-time education, or no, has been coded as 1. This means that we'll be predicting the odds of not being enrolled in full-time education, as an answer of no has been given the larger internal value code. The categorical variables coding table shows us the frequencies of respondent satisfaction with their placement in education, work, or training. In addition, it also tells us that there are 3 categories of S1Q4, and they've been recoded in our logistic regression as dummy variables. In logistic regression, just as in linear regression, we are comparing groups to each other. In order to make a comparison, one group has to be omitted from the comparison in order to serve as the baseline category. In our logistic regression, no has been selected as the baseline or constant dummy variable to which we'll compare the predictions for yes and to some extent. Therefore, no won't be included in our model. You can see this reflected in the table because it isn't coded with 1 in either of these cases. This is because it is the baseline comparison category and hasn't been included in the model. The output tables in Block 0 beginning block show the full-time education enrollment predictions before the addition of our independent variable S1Q4. Block 0 shows us the odds of a respondent not being enrolled in full-time education without the influence of placement satisfaction. In the variables in the equation table, we can see the odds of not being enrolled in full-time education. These odds ratios are presented as the XB output in this table. We can see here that without the addition of placement satisfaction, the odds that a respondent would not be enrolled in full-time education are 0.224 the odds that a respondent would be enrolled in full-time education. In the variables not in the equation table, we can see the predicted significance for the variable S1Q4. If p is less than 0.05, this table predicts that placement satisfaction will be significant, and that the addition of this variable will improve the fit of the model. Before we can move on to the logistic regression that includes S1Q4, we should take a look at the information provided for us here. We can see that the predicted p-value for S1Q4 in this model is 0.000, meaning that it is predicted to be a statistically significant addition. The Block 1 output tables show us the results of our logistic regression including both S2Q10 and S1Q4. The Omnibus Tests of Model Coefficients output table shows the results of a chi-square test to determine whether or not placement satisfaction has a statistically significant relationship with enrollment in full-time education. This chi-square has produced a p-value of 0.000, making our placement satisfaction model significant. We can use the Cox and Snell R-squared, calculated in the model summary output table, to gauge how much of the variation in full-time enrollment is explained by this model. In this example, the R-squared is low at 0.079. This shows us that only 7.9% of the variation in enrollment in full-time education is explained by Sweep 1 placement satisfaction. This suggests that there are other factors influencing a respondent's enrollment in full-time education. Finally, let's take a look at the variables in the equation output table. S1Q41, or the category Yes, has a p-value of 0.000, making it significant at the p is less than 0.05 level. S1Q42, or to some extent, also has a p-value of 0.000, telling us that it is also a significant predictor of full-time enrollment in education. Remember that in this model, No was selected as our baseline comparison dummy variable and is called S1Q4 in our model outputs. Because S1Q41, or Yes, I feel I got the place I wanted, has a p-value of 0.000 and is a significant predictor of the odds of enrollment in full-time education, we can use the odds ratio information provided for us in the XB column here to say that a respondent who was happy with her placement in Sweep 1 has odds of not being enrolled in full-time education that are 0.097 the odds of someone who is unhappy with their placement. This means that those who are happy with their placements are more likely than those who were unhappy to be enrolled in full-time education. This is because an odds ratio of less than 1 means that the odds of an event occurring are lower in that category than the odds of an event occurring in the baseline comparison variable. Because an odds ratio of 0.097 is less than 1, this means that the odds of not being enrolled in full-time education are lower for those who are happy with their placements than for those who were not. In addition, SPSS has calculated confidence intervals for us. Confidence intervals allow us to extend out analyses from the samples in our data to the population as a whole. We can say that with 95% confidence, that for the entire population of England, young people who were satisfied with their placements in Sweep 1 have odds of not being enrolled in full-time education that are 0.080 to 0.117 the odds of people who were not satisfied with their placements in Sweep 1.